Hello. This is the second of two segments about data analysis in the clinical trial. Today I'm going to be talking about binary outcomes. I've purposely chose to first present the concepts for linear regression with a measured outcome, and secondly to discuss binary outcomes because the methods I'll be discussing in this segment build upon the intuition and the methods that we described in the segment on linear regression. So when you're working with binary outcome, you could start by asking about the measures of association. And three measures are used in the analysis of binary outcomes: the risk difference, the relative risk, and the odds ratio. I'm not going to discuss these measures of association in any detail here. I'll remind you that you're expected to have a background in introductory biostatistics for this course. If these terms are not familiar to you, then this would be a good moment to stop and read a little bit about these measures of association for binary outcomes. What I'm going to be focusing on in this segment is multivariable analysis with binary outcomes. Specifically, I'm going to be talking about logistic regression. So the example I'm going to use to illustrate the idea is a study of methods for preventing microbial colonization of catheters in hospitalized patients. So this was a clinical trial that compared two treatment regimens to prevent microbial contamination of central venous catheters. It actually appeared in the New England Journal in 1999. And so in this randomized trial, the investigators compared the rates of catheter colonization in central venous catheters that were impregnated with two treatments: chlorhexidine plus silver sulfadiazine or minocycline plus rifampin. And the objective, of course, was to reduce the rate of colonization. Let's take a look at the univariate results from this study. So first a point: for small to moderate sample sizes, we would use Fisher's exact test to compare the proportions of catheters that are colonized. If the sample size is of moderate size, we would use the adjusted chi-squared statistic. And if the sample size is large, say more than 150 patients in each group, something like that, then we could use the unadjusted chi-squared statistic and we would get very similar results. Let's see how that works in the case of these data from the trial of catheter colonization. Here in this table, you see that the columns are each of the treatment groups and the total numbers of patients. You see in the right-hand side that there were 738 patients in total, and 115 of those patients experienced catheter colonization. Now let's look at the results by treatment group. You see that in the chlorhexidine arm, there were 87 colonizations, that's 22.8%, whereas the minocycline plus rifampin arm, there were 28 colonizations, only 7.9%. So we see that the ratio of colonization was about 3-to-1 here. Now let's do some univariate data analysis. First, I've shown you the three test statistics that I've mentioned on the previous slide: Fisher's exact test, the uncorrected chi-square, and the corrected chi-square. And the thing to notice here is that these three tests are concordant. They all show a very highly significant association between treatment and risk of colonization. Also notice that the uncorrected chi-square 30.14 is very similar to the corrected chi-square 30.02. So with this sample size and numbers of events, the three methods are very closely in agreement. Now, I've chosen here to present the odds ratio because it's the measure of association most naturally used in discussing logistic regression. And we see that the unadjusted odds ratio here is 3.44. We notice that the 95% confidence interval is 2.18 to 5.37, highly significant. So we can conclude that with 95% confidence, the association between treatment and risk of colonization is at least 2. Now, let's turn to the multivariable analysis of these data. So to model the effects of covariates on the probability of a positive response, we need a generalization of multiple linear regression. And the most widely used generalization is known as multiple logistic regression. And multiple logistic regression assumes that the log of p over 1 minus p is a linear function of the covariates. By the way, now that is the natural logarithm of p over 1 minus p. And the nice thing about the logit transformation, or this transformation I've shown you here, is that as p varies from 0 to 1, the log of p over 1 minus p will vary along the entire real line. So it means that any value of log of p over 1 minus p gives a valid estimate of the probability that will be in the interval 0 to 1. As I already suggested, log of p over 1 minus p is called the logit of p. We assume that the log of p over 1 minus p can be written as a linear function of the covariates. So here we have the covariates xij, the ith patient, the jth covariate, and we see that the logistic regression model assumes that the log of p over 1 minus p can be expressed as alpha, the intercept, plus a linear combination of the covariates weighted by their regression coefficients beta j. This can be written also in terms of the probability of success. So if we solve that expression for p, we get that the probability of y equals 1, given the covariates x, is written as this ratio I've shown you here. And you'll often see this expression for the logistic regression model, where beta prime x is a shorthand for the sum of beta j times xij. Now I've shown you graphically an example of how the logistic regression function behaves. In this example, automobiles have been grouped by their weight. And you see the x-axis is the weight of the automobiles, varying from 2,000 to 4,500. And all the makes of car included in this study were grouped into small subgroups based upon their weight. And you see the X's there represent the proportion of automobiles that had poor mileage for the different weight groups. You see that for the group that was about 2,100 pounds in weight on average, you see that only 1 or 2% of the automobiles, according to that graph, had poor mileage. Whereas if you go over to, say, 4,000 pounds, you see that the two groups that are close to 4,000 pounds in weight have have proportions with poor mileage in excess of 90%. So when we classify the cars into these groups based upon their weight, we see that there's a strong association between weight and the likelihood of having poor mileage. And you can see that, in fact, the logistic regression function drawn here actually provides a very good fit to the proportion of poor mileage vehicles as a function of weight. Now, the logistic regression model was developed in the late 1950s and was popularized by its use with in the analysis of the Framingham Heart Study. And one of the things that has been shown again and again over time is that it provides a very informative and reliable way of describing the effects of several covariates on the probability of a positive outcome. And here we see a simple example of that in the context of the mileage of vehicles. Now, let's say a bit more about multiple logistic regression. So imagine that we have an indicator variable for treatment group. How will the model describe the difference in the probability of response for those when x is equal to 1 compared to those for whom x is equal to 0? Well, let's do that on the logit scale. The logit for patients belonging to the group with xi equals 1, you can see is alpha plus beta 1 plus beta 2 times the second covariate xi2. Compare that to the logit in the group with xi equals 1. If xi is equal to 1, the term involving xi will drop out of the model, and so what remains is just the term alpha plus beta 2 times xi2. So what is the difference in the logits for patients with xi equal to 1 versus patients with xi equal to 0? You can see that that's a very simple arithmetic operation, and the answer is beta 1. So beta 1 represents the natural logarithm of the odds ratio for an event in group 2, those for whom xi is equal to 1, relative to group 1, those for whom xi1 is equal to 0, adjusting for the value of xi2. So it is the conditional logarithm of the odds of a positive response controlling for the other covariates in the model. Now let's turn back to the study of antimicrobial catheters. So I'll remind you that the investigators in this study were looking at several covariates, so they used multiple logistic regression to estimate the effects of those risk factors on the incidence of catheter colonization. And they used what we call a step-up approach to building the model. Variables that were significant at a p-value of 0.25 or less in univariate analysis were entered into the model in stepwise fashion till they built the multivariate model. And here was the results of their step-up regression. First, you see in the first row the indicator variable for treatment group. You see that patients that were in the group designated here as chlorsilv had an odds ratio of 2.8 in the multivariate model compared to the comparison group. So again, approximately 3 times the odds, but remember that the unadjusted odds was 3.44, so we see that the adjusted odds ratio is slightly smaller, but still very highly significant. Notice that there are 4 other covariates in this model that enter in a statistically significant fashion. If the patient's catheter was in the femoral vein, there's about a 3-fold risk of colonization. If the patient was in an ICU setting, it's a 2.6 times odds of colonization. Men were about 2.5 times as likely, or their odds were 2.5 times as great to be colonized, and patients who were mechanically ventilated had twice the odds of infection as those who did not. So now a few points about modeling the effects of covariates. First, covariates can modify treatment effects in 2 important ways. First, they can cause confounding, that if there are other risk factors that influence the risk of the response, and if we don't consider those covariates in the analysis, then we can have bias in the estimate of the treatment effect. Of course, the great strength of the clinical trial is that by randomization, we've balanced the treatment group both with respect to both measured and unmeasured covariates, and so the likelihood of confounding is minimized. Another important issue is that there can be effect modification. By effect modification, I mean that the effects of treatment may not be constant across subgroups defined by the covariates. So for example, the effects of treatment may be different for men than for women. And one has to address that problem by introducing terms to capture effect modification in the model. And though epidemiologists often use the term effect modification, statisticians are more likely to refer to this phenomenon as interaction, and so we say that we have to introduce interaction terms into the model to test for effect modification. Finally, I'd like to say that prognostic factors may be more important than treatment, and here's an example from a study of survival in patients with non-small cell lung cancer. And I've shown you 2 covariates, limited disease compared to extensive disease, and performance status, where 0 is the best performance status and 3 is the worst. Notice just in the patients with limited disease, the median survival is 50.9 weeks for patients with performance status of 0 and only 4.9 weeks for patients who are in performance status 3. If you also make the comparison between limited disease and extensive disease, you see that for patients in performance status 0, the median survival is about half as long for patients with extensive disease. So here's an example in which you have 2 very, very powerful covariates that influence the outcome in these patients, and they have to be considered in the analysis. Finally, I'd like to mention that when we're doing logistic regression, we do have to give some thought to the adequacy of our model. And I mentioned 2 ways to assess the the goodness of fit of the model here. First, is the relationship between the logit of response and the covariate linear? Well, one way to investigate that is to add quadratic or other nonlinear terms to the model, for example, the square of the covariate, to see whether those covariates enter the model and signal that you have a nonlinear relationship. You also can group the data and do graphical work, do some plotting to see whether the relationship appears to be linear. And remember that plotting should be on the logit scale. Then there is an important goodness of fit test globally for the model. It's known as the Hosmer-Lemeshow test for goodness of fit. Now, the way the Hosmer-Lemeshow test works is that you divide your patient sample into groups according to their estimated probabilities. So rank the patients from lowest to highest estimated probability based on the model and divide the patients up into groups. A very common choice is deciles. So the top decile, the highest decile, will be the 10% of the patients with the highest estimated probabilities and so on. Then what you can do is compare the sum of the estimated probabilities to the observed numbers of events in each one of those deciles, and you actually can perform a chi-squared test with 8 degrees 10 minus 2, or 8 degrees of freedom, to test whether globally the observed proportions are consistent with the estimated proportions. Now, the Hosmer-Lemeshow test doesn't tell you whether there are other covariates that should be added to the model. It only tells you whether, for the covariates you've included, the estimated proportions are consistent with the observed proportions when patients are grouped in this way. So that brings us to the end of the segment on binary outcomes, and now we're proceeding systematically. In the next segment, I'm going to be talking about time to event outcomes, and these will comprise the 3 most important types of endpoints that we encounter in clinical trials. Thank you for your attention.